In this video, we want to talk about implicit partial differentiation. Now, at the end of the previous video, we talked about how we can view the chain rule and let us see how implicit differentiation worked back in Calc 1. Now I want to do a similar thing, but rather than doing implicit differentiation, I want to do implicit partial differentiation. So the situation is this. Rather than having z as a function of x and y, z is a function of two variables, I'm going to have x, y, and z all mixed together in one equation where it's either impossible or impractical to solve for z explicitly, right? And yet we still want to think of z as a function of x and y and find tangent planes or whatever, so to be able to use the partial derivatives even though we don't have z explicitly written as a function of x and y. I mean, a very simple example would be like a sphere or an ellipsoid. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1, right? That would be an ellipsoid centered at the origin. It's a very nicely smooth surface. At every point there is a unique tangent plane. And if there's a unique tangent plane, then you can look at the slope in the x direction and the slope in the y direction. The problem is, it's not a function, right? It's not the graph of a function because for each x and y, there's two z values. How do you deal with that, right? And this is what we call implicit differentiation. We have the function implied, and we take the derivative of it implicitly. And in this case, because we're thinking of it as a function of two variables, it is partial derivatives. So here's the situation. We've got an equation with x, y's, and z's in it, and we write it in a way that you move all the variables to one side and leave at most a constant over there. That constant might be 0, but it might be any other constant. It doesn't matter. So you get this equation. The graph of that equation will be some surface out in three-dimensional space. If we could solve for z, right, then we could just do what we did before to find partial derivatives. But what I'm going to do now is I'm going to say, I'm going to think of z as a function of x and y and just take the partial derivatives of both sides of the equation. Take partial with respect to x, then come back again, take the partial with respect to y, and see if I can get the partial of z with respect to x and then y out of this. Right? So this is going to be a little bit tricky because I have to consider things in two different ways. Right? I'm going to first look to see if I can find the partial of z with respect to x. So I'm going to take the partial of z, so partial of both sides of this equation with respect to x. Okay. Now the partial derivative of a constant is 0, so that side's easy enough. Now this side, you got to keep in mind how I'm thinking of this. I'm thinking of x and y as independent variables, and I'm thinking of z as a function of x and y. So actually the diagram is here, that this function f is a function of x, y, and z. And then there's x and y, which all three of these are functions of. Right? X is just x, y is just y, and z is some unknown function of x and y, but I'm thinking of it as a function of x, y. It's not independent. Right? So when I take the partial derivative of a z with respect to x, then that's not going to be 0, right? Because they're not independent. So here we go. How do you take the partial derivative of a function of three variables with respect to x? Well, the diagram, right? You got 1, 2, 3 paths from f down to x here, and so here we go. It's the partial of f with respect to x times partial x, partial f with respect to y times partial y, partial x, partial f with respect to z, partial x. That's the 3 paths going down, right? And of course that was equal to 0. Now, partial x, that's 1, right there. Partial y, partial x, well, that's 0, right? Y is equal to y, and it's independent of the variable x. And so the partial derivative there is 0. So that this whole term disappears. You don't see it down here. And then you've got the partial of f with respect to z times partial z, partial x. And again, this is not 0 because I'm not thinking of z as independent. I'm thinking of z as dependent. And whatever that function is, it will have a partial derivative with respect to x. Okay. And now I can just solve for partial z, partial x by subtracting the minus f of x over and dividing by, not f of x, but the partial of f with respect to x and dividing by the partial of f with respect to z. This looks a lot like what we got in the last video, except it's a partial derivative now and not a full derivative. Now, in this notation, it looks a little bit funny to me because I'm looking at partial z, partial x as a fraction, change in z divided by change in x. And what I have is something with an x on the top and a z on the bottom when it was the other way around. But remember, this f sub x is the partial of f with respect to x. And this f sub z is the partial of f with respect to z. And if you think of how do you divide a fraction by a fraction, the one on the bottom gets flipped upside down and multiplied by the top, so that partial of z will end up on the top, partial of x is on the bottom, and the partial f's cancel out, and you get this. Now, yeah, there's a minus sign in there. This is the nature of, well, it's going to be related to the gradient that we see in the videos next week. Okay. So that was the partial with respect to x. Likewise, I can do the partial with respect to y. So starting again with my original f equals c, I'm going to take the partial derivative of both sides with respect to y. Right. So it's partial f, so I'm doing from f down to y now. So through x, through y, through z, so partial f, partial x, partial y, partial f, partial y, partial y, partial y, partial f, partial x, partial f, partial z, partial y. And that's equal to the derivative, or partial derivative of c with respect to y, with, of course, the derivative of a constant is 0. Okay. Now, this is a lot like the last calculation, but kind of in reverse, in that the partial of x with respect to y is 0, and the partial of y with respect to y is 1. So this one disappears, and then this is just 1 times partial of f with respect to y. And this thing right here, partial of z with respect to y, again, we're not thinking of these as independent variables. We're thinking of z as a function of x and y, so it has a partial derivative, a non-zero partial derivative. Well, it might be 0, but probably not. And so it's right there. That's the thing I'm trying to solve for. So subtract f sub y, divide by f sub z, and you get that the partial of z with respect to y is minus partial of f with respect to y, divided by the partial of f with respect to z. Let's do an example. This example is one of my favorite surfaces. It's a little variation of my favorite surface just because I wanted to spice things up a little bit here. This is the graph of the surface. It is sine x plus cosine y plus sine z equals 0. And I want to take a look at the point 0, pi over 2, 0, and see if I can come up with the equation of the tangent plane. Right, I remember from last section or a couple sections ago that the equation of a tangent plane, I need to know the partial of z with respect to x and with respect to y, and then I can use those as coefficients to come up with the equation of my tangent plane. So let's just do a quick look at what this graph looks like. So the point is the dark point right there, and if I move it around, you get a little better view of what this graph looks like. Right. This graph just continues over and over again. This piece right here, you can just keep repeating it in the x direction, in the y direction, in the z direction. It'll fill space with this really honeycomb kind of surface. And I want to just find the tangent plane at a point. I could do this at any particular point. I'm picking this one just because calculations are a little easier, but you get the idea of what it will look like. So I need to know the partial of z with respect to x and with respect to y, but it is really inconvenient to try to solve for z here. Not impossible. There's a little bit of a weirdness because the trig functions aren't really invertible. But since I know what point I'm at, I could use the appropriate arc sign shifted, to the right place. But it's easier just to do this implicitly, right? So in order to do the partial of z with respect to x, I need minus the partial of this thing with respect to x divided by partial with respect to z. So the partial of this with respect to x would be cosine x plus 0 plus 0. So let's just cosine x with a minus sign. That minus sign's right there. And then divide by the partial with respect to z, so 0, 0, cosine z. Evaluating it at the point I'm interested in, so plugging in a 0 for x, pi over 2 for y, and 0 for z. Well, I guess there's no y's in there, but so I got minus cosine of 0 over cosine of 0, which is negative 1. So the slope, whatever the surface is, at that point, in the x direction, the slope is negative 1. Likewise here, doing the partial of z with respect to y, taking the partial here of this thing with respect to y just gives me a negative sine y. And then dividing by the partial with respect to z, that would just be, again, cosine z. And notice there's a minus sign here, and it was negative sine y, so the minus minus is going to cancel out here when I plug my point in. So I've got y is pi over 2 now, so sine of pi over 2 over cosine of 0 is 1 over 1, which is 1. So in the y direction, the slope is 1, whichever direction that is on that picture. Okay. And so I can write down the equation of the tangent plane. Actually, let's scroll down here to see the picture too. This is z equals, this is the z value of the point I want to go through, that's 0, minus 1, so it's actually plus the slope in the x direction, which we calculated was minus 1, times x minus the x coordinate, plus the slope in the y direction, which is 1, times y minus the y coordinate of the point. And simplifying that a little, I have z equals minus x plus y minus pi over 2. And I have plotted that. This is the picture. It looks really weird, again, because the computer has trouble deciding who's on top when they're drawing this thing. Again, it's easier to see if we move it around a little bit. Right. So that at that point, that blue plane really is doing the job of playing the role of the tangent plane, right? It just nicks the surface there. Well, I mean, it crosses through in other places, but it has the same slopes in the x and the y direction at that point. Right. This is very much like what we did back in Calc 1, but now we can do it with multiple variables and partial derivatives.